Nope. Sorry, give me a second to set up the string. All right, so if you want to show something, a function is one-to-one, we're always going to start with, let's say that there exists x, y, x1 and x2 that are in the domain, where we assume our fx1 equals to fx2, and then want to show that x1 equals to x2. That's the general strategy you want to prove one-to-one. So this should be straightforward. We'll just substitute this in, and then I'm going to just do some algebra. All right, and then therefore f is one-to-one. All right, and let's look at the second one. So the second one is if R equals to R inverse, then R is symmetric. All right. So is there anyone wants to take a shot at this one? So let's look at this one together. We have the assumption saying that R equals to R inverse. So that basically means that like the any pair that exists in R, the inverse of that pair should be also exist in R inverse. So let A and B belongs to R. Then we know that R, A and B also belongs to R inverse. Just because of assumption. And then since A and B is in R, and by the definition of inverse, we know that B and A has to be in R inverse. And then therefore R is symmetric. Why R is symmetric? Because you have both A and B in R inverse and B and A in R inverse. All right, any question? The next one is another one to prove or provide a counterexample. So we have R equals to AB, A is not equal to B. So it claims that R is symmetric and transitive. All right, and we want to first to say if this one is true or false. So we can see that so let's just check for some pairs. So if we let like let's see pair 1, 2 in relation R, and then just by this statement 2, 1, and 1 must also be in R since it is symmetric. And if R is transitive, we also need that 1, 1 is in R, but that actually violates the definition of the relation R, where like your A cannot equal to B. So the relation is not transitive, and thus this is a false statement. All right, any question on this one?
I just have a quick question. Are you getting these from the practice quiz?
Yes, it's exactly the same question on the practice quiz 4.
Got it. Thank you.
Yep, and it's on Canvas. You can download the PDF.
I have a question.
Uh-huh.
So is this a prove or provide counterexample? So if the statement was true, then we mention the counterexample, right? But if it's false, we just leave it as it is.
So if it was true, you can just like write your formal proof, and if you think it's false, you would just provide a counterexample. Yeah.
Okay, thank you.
All right. So the next one, I'm gonna write this out. We have the relation R on the set S, where the set is 2, 3, 4, 5, and all the way goes to 11, 12. And given by R equals 2, AB belongs to S cross X, S cross S, and A is divisible by B. And the first one is, so this one is also prove or provide a counterexample to the propositions below. So the first one can claim that the relation is reflexive and B is anti-symmetric and C is transitive. All right. So I'm just gonna give you guys about 2 minutes to look at the first three. All right, so part A should be straightforward. We have the definition of R as A divides B. So we know if we let let's say X belongs to the set S, and then it should be for any X in S, X always divides itself. And then thus XX is in R. And then therefore R is reflexive. So this one is actually true. And then what about antisymmetric? So antisymmetric means that you cannot have a pair that is symmetric. So if we start with so this one's actually true as well. Let me move this below. So just by thinking about this, we actually can have the pair 2, 3, and well, let's say like 2. All right, so why don't we just start this one? So let X, Y belongs to X, S be given so that our X is not equal to Y, and XY is in R. So we start with this one and we assume that XY is in R. So we know that X divides Y. And then since that in the assumption right here, we have X is not equal to Y. So we cannot actually have the case that y is also divisible by x. So we know that y, x cannot be in R. This is just by the definition of Division Theorem. And therefore, R is antisymmetric. All right, if we any question on this part? All right, so for transitive, just by the definition, we're thinking about if xy, if both xy and yz are in the relation, then xz must be also in the relation to satisfy that it is transitive. So for this one, if we just start with that x, y, and z belongs to s, and then we assume that x, y, and y, z are both in R, then just by the definition, we know that x is divisible by y and y is divisible by z. And by the definition of the division theorem, we know that x is also divisible by z. If we just write this out in more detail, we can say that x divided by y, that means x equal to say some k1 times y, where k is integer. And y is equal to some k2 times z. So if you look at if we just, let's see. Oh, I think I just write this inverse backwards. It should be backwards where see, where it should be y equals to x times k1 and z equals to y times k2. Okay, and then if we just replace, we have that z equals to y dot k2, and if you just replace y with x dot k1 and dot k2, and by closure, this is just k, where we have k equals to k1 dot k2. And thus you can say x divides z. And therefore xc is in R. All right, any Any question? Okay, so the next part is asking if R is a strict order on S. So what does it mean to say that a relation is a strict order? So what are some conditions that need to be that you need to satisfy? Anyone remember?
Irreflexive, antisymmetric, and transitive.
Yep. So it is irreflexive, and so I think the one you're talking about is strict partial ordering. Is that correct? So there's actually strict partial ordering and a strict total ordering. So I think right here, we're just talking about like a strict total ordering. But yeah, so it is irreflexive, and antisymmetric, and transitive. So the only difference between like a total, so a total ordering is that it is like a partial ordering, but also you have the, for every A and B in the set, if A is not equal to B, then we have like either A and B in R or B and A in R. So that's just only one difference than the partial ordering. But yeah, for this one, we only need to satisfy this 3 conditions, and where we can say that no. So this one is not a strict order since R is reflexive. All right, so the next one is R a partial order or a total order? So what do you guys think?
Wouldn't it be a total order because when A divides B for all the values in S, we found that B doesn't. Oh wait, maybe not. Never mind. I think I mixed it.
So Okay, so let's talk about this one. So if R is a total order, then let's just check if it contains like all the variables in it. So if R is a total order, we know that besides it is a partial ordering, so R is a total order if it's partial ordering and it satisfies the condition we just talked about, like for every A and B in A. If A is not equals to B, we should have either AB in R or BA in R. That just means we need to have at least one of them in the relation. So a partial ordering is that it has to be antisymmetric, transitive, and reflexive. So a strict partial ordering has to be irreflexive. All right, and if we just look at our R in this case, we have shown that R is reflexive and it is antisymmetric. Sorry, this one is transitive, antisymmetric, and reflexive. So we know that R is a partial order on S. And then if it's like, if we want to show that R is a total order, so what are the pairs that, can you just give out like an example, like is actually not in R to make the to meet the definition of a total order? So can you just give out one example saying that?
Couldn't that be like 3, 4? Because 4 doesn't divide 3. Or 3 doesn't divide 4, I mean.
Yep, exactly. So in this case, our AB would be A equals to 3 and B equals to 4. And then they are both contained in A. And we know clearly that A is not equal to B, but neither 3 and 4 or 4 and 3 is in R. So R is not a total ordering. All right, and the answer to this one is R is a partial ordering. All right, any question on this problem? Okay. All right, so if we look at question 5, we're given two sets, 0, 1, 2, 3, 4, 5, and B is 0, 1, 2, 3. So the first claims is that there is no possible function f A goes to B that is 1-to-1. And this is true. Why this is true? Because you cannot actually create a function that well, just by looking at the domain and codomain. The number of, you cannot actually create out that function to make it 1-to-1. So where every element maps to like maps to another element, another distinct element in its codomain. So this one is not 1-to-1. And part B asks if, so there's no possible function f a goes to b that is onto. Well, this one is false. I can actually construct a function like that. So let's see, f is a goes to b, where we can define the relation as a b belongs to R a cross b, where our let's see that this works. A is smaller or equal, well, A is greater or equal to B. So this one is actually a onto function. All right. And for C, we have our G as the set of order pairs 0, 0, 1, 2, and 2, 1, and 4, 3, and 5, 3. And we claim that is a function from A to B. So this one is actually false. Is a function from A to B. Why it is false? Anyone wants to give a reason about why this one is false?
3 doesn't have an ordered pair as the domain. Like
Yep.
for a function, it has to have every member of the domain mapped to the codomain.
Yep, exactly. So every number in the domain has to be mapped to a number in the codomain. And in this case, in G, we don't have a ordered pair that 3 goes to anything. So this was not a function from A to B. And so for D, it says we're given like a relation R with domain B and codomain B, and R is defined as 0, 1, 1, 2, and 2, 3, and 3, 3, and 3, 0. So the first one, we just want to check if R is transitive and antisymmetric and reflexive. And if Rfr is antisymmetric. So let's just look at the first one. Is R transitive? So if R is transitive, we can say that we have the pairs where 0 goes to 1 and 1 goes to 2. If R is transitive, that means like 0, 2 has to be also in R as well. So nope, R is not transitive, since 0, 2 is not in R. And then is R antisymmetric? Yes, R is antisymmetric. For the other pair that A is not equal to B, we cannot find both AB and BA in R. So R is antisymmetric. And reflexive.
Can you repeat that again?
Yeah. So if A is not equal to B, we cannot find an outer pair that both A and B and B and A contain in relation R. So which means it is antisymmetric.
Okay, thank you.
Mm-hmm. All right, so for is it reflexive? And clearly, nope, it is not reflexive. And the last one asks, is Rfr antisymmetric? So why don't we just write out what is Rfr? Let me copy and paste. All right, so Rfr, if we just take the set 0, 1, and then 0 goes to 1, and then in this case 1 should go to 2, so that means 0, 2 is in Rfr. And then similar for 1 and 3. And 2 and 3, and 2 and 0. And we should also have, let's see, 3, 3, and 3, 1. All right, and that's our Rfr. Okay, so is this one antisymmetric? Nope, this one is not antisymmetric. And just by the definition, as said, if we have A is not equal to B, we cannot have both AB and BA in R. But in this case, we have 0, 2, and 2, 0, and 1, 3, and 3, 1 to make it not antisymmetric. But it is not symmetric neither. So since we doesn't have 3, 2. So Rfr is not antisymmetric. And it is also not symmetric. All right, any question on this part? And 3, 0. I don't think we have 3, 0 in Rfr. Are you talking about Rfr?
Yeah, I am. Because wouldn't you have R, you should have 3, 3,
Yeah.
and 3, 0. Wouldn't that give you 3, 0?
Yeah, you're right. Sorry. Yeah. We should have 3, 0 in Rfr. So if 3 goes to 3 and goes to 0, yeah. Yeah, you're correct. Yep. All right. So the next part, we're still talking about this question, but the last part is that let R be a relation with domain A and codomain A, where we defined as xy belongs to R if x mod 3 equals to y. And we're asking about, is R antisymmetric? So in this case, all right, so, and this one is yes. So R is antisymmetric. So does anyone have a question about this one, or I'm just going to move to the next question. Okay. So the next bigger question is, we have Fr goes to R where Fx equals to x squared. And we want to prove that we want to either prove that F is 1-to-1 or provide a counterexample. And prove F is onto or provide a counterexample. So if f is 1-to-1, that means every element in the domain so we can actually draw the, let's just draw the graph of x squared. So if it's 1-to-1, we want to make sure that every element in the domain that maps to a unique element in the codomain. So in this case, we were taking this line. Let's say right here, if it is 4. And then we actually can find 2x, where x can be either -2 or 2. So this is a counterexample to claim that f is not f is 1-to-1. So the first one is nope, f is not a 1-to-1. Since we can find 2 elements in the domain that maps to one element in the codomain, and it's not 1-to-1. All right, and for onto, we want to make sure that there's not all the elements in the codomain that are mapped to. So if we take -1, we actually cannot find any x that maps to -1. That belongs to, so we cannot find any x in real number that makes fxy equals to -1. So f is not onto. And this will just be your counterexample. And then the part 6 asks if f is 1-to-1 correspondence. So 1-to-1 correspondence just means that f needs to be both 1-to-1 and onto. And since we already showed that f is not a 1-to-1 and not onto, so it is not a 1-to-1 correspondence. All right, so it seems like we still have questions 7, 8, and 9 left. So are there any particular question you want me to go over any of the part from that 3 question, or I'm just going to stop the review here? You can always look at the solution on Canvas as well. Okay. All right. If there's no other questions you guys want me to go over, then yep. So this is the end of our review. And good luck on the exam.